All right, everybody, welcome back. We're going to do a lesson on titrations today. So titration is actually mathematically, well, for our class, identical to dilutions. So first, let's talk neutralization because we are dealing with acids and bases. When an acid reacts with a base, it's going to be a neutralization reaction. And if you have just the right amounts of both, then when the acid does react with the base, you are going to produce simply water and some sort of salt. It doesn't have to be sodium chloride like that example there, but it's going to be some sort of ionic salt and water. And this is going to be true as long as we're dealing with simplistic forms. Well, it's kind of always true to some extent, but for our class, not higher levels of chemistry, but for our class, we're going to stick to the simple strong acid and strong base type of neutralization reaction. There are more complicated ones when you start dealing with weak stuff, but we're going to ignore that and pretend they don't exist, much like a lot of things we do in life. All right, but the example there, hydrochloric acid with sodium hydroxide produces water, H2O, and sodium chloride. So this is really just salty water is what's left. Speaking of, because those salts that were just mentioned actually are just spectator ions, if you try to look at the net ionic equation for these acid-base reactions that we're focusing on in our class, which would be strong acid with a strong base together, the net ionic equation is very simple. It's the excess H plus ions from the acid, the excess OH minus ions from the base. They come together, they form water molecules, the end. It's really simple. That's a nice little video that kind of shows that. And the previous slide had another video. You can view those at your leisure looking by opening up the slideshow later on. But I'm going to keep going. So let's talk about what exactly is this acid-base titration. We just talked about a neutralization reaction. Well, acid-base titration is really a neutralization reaction. It's just that you're doing it really carefully and measuring how much volumes that you're adding. So first of all, you need a standard solution. A standard solution is a solution that you actually fully know the concentration of. You know the exact concentration. And you're going to need also some sort of indicator to tell when you've reached the neutralization point, or the equivalence point is what we're actually going to call it. But so how do you know right when you've neutralized? And you're going to either be able to use an indicator, or if you have a very good pH meter, and by me saying very good, there's not a lot of good pH meters. They're very fickle in how and when and how they work. So good luck with those. The standard solution, as you see there, it's the solution that you actually fully know the concentration. The other solution, whichever it is, the other solution is the thing that we don't know the concentration for. But by doing this acid-base titration, we're going to be able to figure it out. And the math is really easy to do so. Okay, so ignore emails that I'm getting. All right, so titration. Basically, you take your standard solution and you're going to add it slowly to your unknown solution. It doesn't matter which one is the acid or base. I think for our examples, our unknown is going to be the acid, and our base is going to be our standard solution that we absolutely know the concentration for, and that's pretty typical. So, and when you finally get to the point where it's completely neutralized, acid and base, they neutralize each other, that's going to be the equivalence point. The only problem is we have giant eyeballs. We're huge things, and these little ions are super tiny. We cannot see them. We have no idea just by looking at a solution when you've completely reacted all of the H plus with OH minus ions. So that's just water molecules now. So we need some help. But before we get to that, let's just expand upon talking about equivalence point. Equivalence point is when you have equal concentrations of H plus ions with OH minus ions, right? So you don't have any excess of one over the other. Another way to say that is the moles of H plus is equal to the moles of OH minus. And again, we're focusing on strong acid with a strong base. And when we do that, the pH is always going to be 7 at that equivalence point. Again, assuming normal temperatures, which we'll always assume, 25 Celsius. Right, so that's the cool thing about strong acid and strong base. Not only is everything else simplified and the math simplified, but we actually already know the pH when it does reach the equivalence point, pH 7. But again, you can't just look at a solution and know it's at pH 7. We need the pH meter or an indicator. So that brings us to this next thing that we're going to identify as an endpoint. Endpoint is simply defined as the point at which an indicator changes color. So if we don't have a pH meter, if we don't trust our pH meter, then we can use an indicator. Indicator changes color at a certain range of pH, right? So we choose the correct indicator to change color around where we want to stop, or, when we want the pH to tell us when to stop the titration. Right? And in our examples for our class, we want the pH to be at 7. That's how we'll know we're at the equivalence point. So we want some sort of color change to happen around pH 7. All right, so it doesn't have to be exactly at pH 7, but just kind of close. Here's a video that kind of shows, you know what, I should actually show this one. Let's watch this one.
A titration is a controlled acid-base neutralization reaction. 20 milliliters of hydrochloric acid of an unknown molarity is added to a flask. 2 drops of indicator dye are added to the acidic solution. This indicator dye is clear in acidic solution and pink in basic solution. The burette is filled with a sodium hydroxide solution of known strength, and an initial reading is taken. The base is added to the acidic solution until the solution stays a slightly pink color. At this endpoint, a final reading is taken. The moles of base added equal the moles of acid present. This same reaction can be followed using a pH meter instead of an indicator dye. Initially, the pH changes very little as base is added. Suddenly, the pH changes rapidly as the endpoint passes. The solution quickly becomes very basic, and again, the pH changes very little. The endpoint occurs at this middle point on the curve.
All right, so that's a good video. It really just shows how you would do a titration. We would normally do a titration with a burette, not with a pH meter though, with an indicator. But we can't do that. And the best we could do would be a simulation, but the simulations aren't very good for these titrations that I've come across, so we won't. But that gives you, I guess, at least a visual on how you would do a titration. Here is a graph of pH versus the amount of your standard solution. In this case, it was a base, sodium hydroxide. And you can see we started with an acid because it's a low pH. And as we added the base, not too much change to the pH up until we got really close to the equivalence point. Then suddenly we have rapid changes to pH. We hit the equivalence point. We had no idea we were there because in this example, we're using a color change, an indicator, and the color change doesn't happen till right around here. Okay, so this phenolphthalein is a very common indicator, one that you have to know, and it changes from colorless, you cannot see a thing, to pink, to ultimately a dark pink color. Right around the pH, basically from pH 8 to pH 10, that's where you see that color changing. Anywhere above pH 10, it just continues to stay a nice dark pink. Anywhere below 8, you can't see anything. It's colorless. So the actual color change happened right here, and that's when we stopped it, which wasn't exactly at the equivalence point, but it was pretty close. It was only a couple of drops difference. And those couple of drops are, as far as significant figures are concerned, aren't going to be really at all different from the equivalence point. So we're good by using that indicator. We wouldn't want to use an indicator that's way up here at a higher pH change. Conversely, anyone really down low where we have a color change at a very low pH, but anywhere kind of nearby this pH 7 indicator, pH 7, an indicator with pH 7 color change, that's good enough. And that phenolphthalein was close enough. Oops. All right, so a couple other indicators you should know. Speaking of indicators, this is labeled indicator. So indicator is by definition a substance that changes color over a narrow pH range. All of them are narrow pH. They're only over about 2 pHs where they change color. Litmus paper is one that you might have used before in science. It's very, very common. So we're including this. It has a specific color change. All of these have specific color change. In litmus papers, or in litmus paper, it is a blue / purpley blue color when it's above pH 7, when it's a base. And when it's acidic, it says red, but really it's like a dark pink color. So it's either dark pink or bluish purple. And that's all you can tell from litmus paper. It's either above 7 or below 7. So it's actually pretty helpful for the kind of titrations that we're doing, because our equivalence point is going to be at 7. Phenolphthalein, that is one that's extremely common because it's not too expensive, and it's really easy for everyone to go from I don't see anything to ooh, I see it, a slight pink color kind of thing. So it's very commonly used for titrations, including for trying to hit the equivalence point at pH 7, even though you go beyond pH 7. Okay, let's move on. So memorize those, please. If we were in class, I would do a demo with red cabbage. You boil some red cabbage leaves and you get some, it's kind of a bluish, it's like a bluish color, maybe a slight purple tinge to it. And anyways, you can use that as an indicator. It's got a whole bunch of different molecules in there that changes color at different colors. So you get a good idea of what pH your solution is just with a little bit of red cabbage added to it. Here's a nice collection, and this does not in any way represent all of the indicators, but it just gives you an idea of just how many different indicators there are. There's lots, and they all have different color changes at different pHs. Some overlap, so there's choice involved. Here's our phenolphthalein right here, colorless to red. If we were trying to get an indicator that tells us when we've gotten about pH 7, that's an option. This one right here, thymo blue, would be an option. Phenol red is an option. You get the idea. So this whole chunk would be good options for to indicate a pH 7. Oops, not what I wanted. So let's do the math. The math is pretty easy, especially if you were paying attention to that last lesson. MV equals MV. That's the exact same math. The only difference today for titrations is instead of dilution and concentrated sides, we have acid side, base side. Base side, that's like where the Saved by the Bell people went to school. It's a good show. You should check it out. All right, let's try one. Titration problem number 1. So we've got 40 milliliters of nitric acid. And look at that. We don't know the concentration of the nitric acid. But we're titrating it with the standard solution of sodium hydroxide. And we know the sodium hydroxide is 0.1 molar. And after we're doing the titration and reaching the endpoint, we've added exactly 35.0 milliliters of sodium hydroxide. So can anyone tell us what the concentration of that original nitric acid solution is? Because after we've added it, now it's, who knows, but it's a neutral salt solution now. But before we added it, what was the original concentration? How do we figure that out? Let's take a look. Here, I made a little document because me writing was bad. All right, I'll flip back and forth. See, the base, here, we'll start with the acid side. 40 milliliters of the nitric acid, and we don't know the concentration. So I'll write the concentration as X. Oh, that's weird. Times 40 milliliters. I'll just leave a little blank there. You know that it's a dot, right? Sure you do. The base, we have 35 milliliters of 0.1 molar. So 0.1 molar for the base, 35 milliliters. Oops. Ooh. Want it all in the same line. There we go. So how do we solve for our unknown concentration? Ooh, we should probably divide 40 milliliters on both sides. So let's divide 40 milliliters on both sides. Let's make a little line here for both. I don't want underlining that one. 40, ooh, hey. There, perfect. And then check it out. The 40 milliliters disappears, right, on the X side. The milliliters unit disappears on the right side. They cancel each other out, leaving us with molarity for our units. Question is, what's the numeric answer? 0.1 times 35 divided by 40. Let's use a calculator. 0.1 times 35.0 divided by 40.0. And we get 0.0875. That's our answer. And that makes sense. That's just a little bit less than 1 molar concentration for our acid, and we needed a little bit less of the base to neutralize the acid. So that actually makes sense. So 0.0875 molar concentration was our original nitric acid solution. Isn't that easy? Yeah. MV. Here's another one. Try this one. Pause the video and see if you can figure it out. What is the concentration of hydrochloric acid solution if 50 decimal point for two significant figures, 50 milliliters of a 0.25 molar sodium hydroxide solution are needed to neutralize 20 milliliters of the hydrochloric acid solution? So what is that hydrochloric acid solution? Pause, figure it out. Okay, you're back. Let's talk about the answer. I believe the answer, I'll just go straight to the calculation of it. Oh, wait, I can't see the answers. 50 and 0.25. 50. That's our standard base solution. And I'm going to divide by the 20 milliliters of our unknown acid solution. We get 0.625. That's the molarity concentration of our unknown acid solution, so hydrochloric acid solution. However, two significant figures means we have to round it off to 0.63 molar. Thanks, significant figures. You got us again. So 0.63, or if you forgot about significant figures, 0.625 molar is the concentration. All right, now you should be able to answer all those questions, including the drawing. Hopefully you get the drawing. If you have any questions on that, I will go over that at some point in the future. So do the titration questions now. Oops.